phi, and theta as our three coordinates. Of course, fundamentally, when we first introduced this coordinate system, we want to use these three numbers to locate points. And right, that's what we do. We have a point, and then we see how long is it from the origin. And this is the angle formed by the ray and the positive direction of z-axis. And this is the angle formed by the projection on the xy plane with the positive direction of x-axis. Right? This work doesn't seem to mean anything. We have a picture that will be much more suggestive. So I have a point right here. So if I line together this point in the origin, and this is the distance given by rho, right? This is distance rho, this is the part, and this is the angle formed by the ray in the positive direction of the z-axis. And then if we project this point back onto the xy plane, so we line these two together, so the projection and the origin on the xy plane. And this is the angle given by theta. Right, so these are the three coordinates, three numbers. Given any three numbers, you can locate a point. Conversely, if you give a point, you should be able to find the three corresponding numbers for rho, phi, and theta. Right? Not only we're using these spherical coordinates to locate points, we're also going to describe solid regions in terms of computing the triple integral d f x y z d v. We also want to put this intervening region in spherical coordinates. All right, so not just the points. So that's the reason. That's the reason why I give you the understanding of what happens if I let rho to fix. Okay, so I let phi and theta to change. What happens? What happens? If your rho is a fixed quantity, you're going to get a sphere, right? So if you allow phi to fix, so rho and theta can change. What happens? You're getting a cone. So you can rotate the theta, you're getting a cone, and you can let rho to increase and decrease, you're going to get a half cone, right? You're going to get a half cone. So essentially, rho is going to be always in a negative. Phi is bounded between pi and 0, and theta can vary from 0 to pi. And theta can vary from 0 to pi. And one of the probably a little challenging part is if I fix theta and I let rho and phi to change, I'm going to get a half plane. You still remember that? So I'm going to get a half plane if I allow rho and phi to change. So these ideas related to the spherical coordinates is pretty helpful for you to understand not only how to locate a point, but also how to relate to regions, and how to relate to regions. And the relation between x, y, z and rho, phi, and theta is x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And z is equal to rho cosine theta. Okay? So these are definitely the equations you want to remember. These are definitely equations you have to remember. Okay? You can remember this from these algebraic expressions. You can also understand that from trigonometry. Right? So as long as you know what rho means, what the phi means, what theta means, putting into trigonometry, you should be able to derive these equations for yourself. Right? We did do that in Monday's class. Questions? Any questions? We can get these three equations coming from trigonometry. Questions? Okay. So next, I want to write down this into a into a spherical coordinate system. So if I want to write it into rho, phi, and theta, I have to change x, y, z into rho, phi, and theta. All right? So that's a very natural requirement. So I have rho sine phi cosine theta for x, rho sine phi sine theta for y, and rho cosine phi. So I can easily switch between x, y, z and rho phi theta by this formula. But also I have to worry about what happens for the intervening region in the spherical coordinates. All right? So how do I describe this D in rho phi and theta? And that is depending on individual problems we'll discuss in a minute. So I have to worry about what the range is for theta, what the range is for phi, and what the range is for rho in order to describe this intervening region, all right? And usually we have this experience for polar and the cylindrical coordinate system. If we switch between x, y, z and some angles, some extra factor is gonna come, all right? Some extra factor is gonna come. For spherical coordinate system, the factor is rho squared sine phi. D rho, d phi, and d theta. Okay? So as long as we're still doing this triple integral in the spherical coordinate system, there are three things you have to worry about. First is the easiest. You just need to change x, y, z to rho, phi, and theta in this formula. So definitely have to remember what the formula is in order to do that. You just need to plug in. And this step is usually the easiest because a lot of times if your function f contains x squared plus y squared plus z squared, that's a big hint. We want to use spherical coordinates, all right? And then in changing into rho, phi, and theta, this function will be extremely easy. So you don't have to worry about this too much. But you have to always remember when you switch between x, y, z to rho, phi, and theta, you have to add one extra factor. Okay? You have to add one extra factor. And usually in triple integral and double integral, the most difficult part is to identify this region. So this is the key part. How do we identify the region? Okay. So switch x, y, z to rho, phi, and theta, add one extra factor, and worry about how do you describe this region. Okay. So I will give you a couple of examples of how to describe this region in spherical coordinates. Okay. So first one is I want to find the volume of ball with radius r. And in fact, we've already done that before. We have already computed the volume of a ball with radius r. We did this in double integral. We actually did it again in triple integral involving z simple region again. You can actually put it into a cylindrical coordinate system. And we know the answer already. So the volume of the ball is equal to 4 pi r cubed divided by 3. So that's the volume of the ball. This kind of problems is really one of my favorites. Okay? Because that really requires you to use calculus into some seemingly trivial questions. Right? And then you realize why calculus is so important in mathematics. Because without it, even a simple question as computing the volume of a ball or the area of a disk is very, very challenging if you don't have calculus as a tool. So these are my favorite questions. When I say they are my favorite, you know what it means, right? It's going to be in a test, right? Oh. So I will give you a problem looking like this, and then you can choose your favorite integral functions you can do. You can use double integral, you can use triple integral, it's up to you. Okay? But usually some of the tools are easier than the other. Okay? Some of them are easier. First of all, I know I want to compute the triple integral of a constant function 1. All right? So this is the volume of the ball. So if I denote D as the ball with radius r, this is the volume of the ball. And then I want to describe a ball in spherical coordinate system by using rho, phi, and theta. All right? By using rho, phi, and theta. And this is already given by here. It's already given here. If I want to cover all the points within this ball, I can allow theta to vary from 0 to 2 pi. I allow rho to vary from 0 to pi. You don't have to go from 0 to 2 pi. It's going to go repeatedly. Okay? Phi covers from 0 to pi will be sufficient to go over all the points. Can remember that. Okay? So this is the angle between the real and the positive direction of the z-axis. If you vary your rho phi to go from 0 to pi and theta to go from 0 to 2 pi, you will be able to already cover all the points in the ball. Can you imagine that? You don't have to go over too much for phi. That's the difference between the range in phi and the range in theta. And naturally, when a radius is capital R, rho will go from 0 to r. All right? So essentially, I'm only computing from 0 to 2 pi for my theta, from 0 to pi for my phi, and from 0 to r for the radius. Okay? And I need to switch between x, y, z to rho, phi, and theta. This function is so easy, I don't need to do anything. All right? But I have to add in one more factor, rho squared sine phi d rho d phi d theta. So this is going to be the volume of the ball. So we did this in double integral. We can do this in double integral. We can also do this in cylindrical coordinate system. But this is the easiest. This is the easiest. Yep.
If on the test we chose, or would we have the option of doing like the revolve method? Because that would be a single integral.
I'm sorry?
So like the revolve method of you get the equation of you know what I'm talking about. That wouldn't be allowed on the test, or?
Well, for me, mathematically, I don't care about which two you use. But unfortunately, in the end, you're going to go for a common final. So sometimes the coordinator will ask you to evaluate triple integral in a particular method. So in that case, you have to use whatever the requirement is. Okay. So here, as long as I write it into spherical coordinates, this triple integral is super easy. All right. This triple integral is super easy. In fact, if I look at the ranges for these 3D independent variables, they're all independent with each other. All right? So here is probably a slightly confusing statement for you. I'm writing it in the spherical coordinate system, but the domain, the integrating domain with this function is actually a cube. Right? If I'm looking at the region in rho, phi, and theta, this integrating domain is actually a cube. So essentially, I'm writing the beginning from x, y, z. It is integrating region with a ball with radius r. But when I write it in rho, phi, and theta, integrating region becomes a cube. And a cube is our favorite integrating region. Okay? So if you don't understand what I'm talking about here, you're confusing about the different geometries. Don't have to worry about that. You just look at this triple integral and do whatever evaluation tools you have to do. Okay? So I'm evaluating this from rho, 0 to 2 pi, 0 to pi, and rho squared sine phi. Rho is the only independent variable, so I'm getting a rho cubed divided by 3 sine phi, and then evaluate from rho equals 0 to rho equals capital R, d phi d theta. Okay?
Wouldn't it be negative p cubed divided by 3 cosine?
No.
Oh, I'm only looking at rho as the independent variable.
Oh,
the phi
that's
here
fine.
is only constant.
Okay.
Right? But eventually phi will come into play.
They both look
right?
the same.
Yeah. And also, I specify my evaluation from rho equals 0 to rho equals r. Right? So that will actually stress the point that rho is the only independent variable. Am I right? Confused?
Well, they look the same.
Yeah, they look the same. That's why I got
Oh, I
confused.
see what you're thinking. Okay.
That's why
You're talking about my Greek alphabet. Yeah.
There you go.
So, probably, yeah. So this is my rho.
They look like keys, I don't know.
So this is my phi. Okay. They're not the same. No, they're not. Right? How do you write it?
Well, that sounds
That's all right?
Yeah, that's fine.
Both ways I write it still look. They look the same.
That's it. Yeah, the rho and phi are different. Well,
Why don't we use like phi, like the capital phi?
they're all lower letters. in
Oh.
Greek alphabet. Okay. I guess it doesn't really hurt if you want to use R, the English letter. It doesn't really hurt that much. But since we're using phi and theta, all Greek letters, let's just keep it consistent. Okay, so here I'm getting 0 to 2 pi, 0 to pi. So I'm having a 3r cubed sine phi d phi d theta. Okay. And then in here, phi is going to be the only variable here. And also, after I eliminate the interior integral, I'm supposed to see no rho anymore. All right? So in this step, there's no rule, so we're happy. And then I'm looking for the antiderivative for sine phi. That's where you find the minus cosine phi as the antiderivative. Evaluate from phi equals 0 to phi equals pi. And then from 0 to 2 pi, I have r cubed divided by 3 d theta. Okay? So this interior function, the intervening function here, has nothing to do with theta. In fact, you're just multiplying by 2 pi after you eliminate the very last integral here. Okay? So here I'm getting cosine pi, that's minus 1, right? And cosine 0 is plus 1, so minus 1 minus minus 1, I'm getting 2 right here, right?
Yeah,
Mm-hmm.
two.
And then multiply by 2 pi in the end, so it's going to be 2 pi multiplied by 2 multiplied by 3 r cubed. That's where we get a 4 pi r cubed divided by 3. Okay? So you can evaluate the volume of a ball in calculus with integrals, but you can choose to use double integral or triple integral. In triple integral, you can in fact use cylindrical coordinate system or spherical coordinate system. A spherical coordinate system, out of all these different methods, will be the easiest. For the simple reason we already agreed on. If the intervening function contains x squared plus y squared plus z squared, or the intervening region is a ball, or some pieces of a ball, then using spherical coordinate system will be much more friendly. Okay? Okay? Yep.
This be the easiest case for a spherical coordinate challenge?
This is probably the easiest. Yeah.
Where did you, the first interval is from 0 to r, where did you find that r? Or where did you?
Oh, this is the condition given in the problem.
Oh, okay.
This is the condition given in the problem. Any other questions? Okay, so here is one independent remark I want to make. So if I'm looking at this triple integral, I'm not sure if I've seen this before. In order to evaluate this triple integral, instead of carrying all the variables with the following steps, I can in fact break down this triple integral into a multiplication of 3 integrals. I can break down this into from 0 to 2 pi d theta, from 0 to pi sine phi d phi, and from 0 to r, rho squared 0. I can in